Okay, let's dive right into this explainer and really unpack the modern AI data stack. If you've been anywhere near artificial intelligence lately, you have probably heard the term vector database thrown around constantly. But what about tensor databases? Well, today, we're exploring the crucial difference between vectors and tensors and why understanding this distinction is absolutely fundamental if you're building scalable AI applications. Here is the quick roadmap for today's explainer. First, demystifying the tensor. Second, vector versus tensor databases. Third, real-world tensor systems. And fourth, the modern AI stack. All right, let's kick things off with section 1, demystifying the tensor. So, what exactly is a tensor? I know, it kind of sounds like some intimidating terms straight out of advanced physics, right? But honestly, before you even touch on databases, we really need to answer this fundamental mathematical question. The good news is, the concept is actually quite intuitive once we break it down visually. At its most basic level, a tensor is just a mathematical object that generalizes things you already know about, scalars, vectors, and matrices, to literally any number of dimensions. The main takeaway here? Just think of it as a massive, flexible container for your data, one that can scale up endlessly in structural complexity across multiple ranks and axes. Let's watch how this actually builds. Step 1 is a scalar. That's just a zero-dimensional tensor, basically a single number. Easy enough. Step 2, we introduce a vector, which is our one-dimensional line of numbers. Then, step 3 gives us a matrix. You can picture that like a standard 2D spreadsheet. And finally, step 4 breaks wide open into the n-dimensional tensor. That's where we unlock 3D cubes of data, 4D structures, and, well, way beyond. Now, why does this matter so much? Well, everything, and I mean everything from input images and audio waveforms to complex neural network weights and attention layers, it's all represented as an n-dimensional tensor. These things are the absolute core data structure in deep learning tools like PyTorch and TensorFlow. They are basically the native language of artificial intelligence. Moving right along to section 2, vector versus tensor databases. So this brings us to a super common roadblock for developers. We hear about vector databases literally all the time, especially with all these ChatGPT integrations, right? But do systems actually exist specifically for these complex, multi-dimensional tensors? The short answer is yes, absolutely, but their fundamental purposes reflect two completely different workloads. Now sure, a vector is technically just a 1D tensor, but in the data engineering ecosystem, we completely split them up. Vector databases are purpose-built to store 1D embedding vectors, mostly for calculating mathematical distance. Tensor, or array, databases, on the other hand, are built to store n-dimensional arrays specifically for multi-access slicing, reshaping, and some seriously heavy linear algebra. When we put these side by side, the difference in their workloads is honestly glaring. A vector database is laser-focused on finding nearest neighbors, finding data that's semantically similar for a RAG pipeline or semantic search. But a tensor database, it is executing complex range queries and transformations on dense or sparse data arrays. The use cases just completely diverge. Vector tools are great for recommendations. Tensor tools? They're powering things like satellite imagery analysis, medical MRI scans, and massive deep learning training pipelines. Okay, section 3, real-world tensor systems. So who's actually building this stuff? Well, here are the heavy hitters driving the tensor and array database ecosystem today. We've got platforms like ActiveLoop, DeepLake, and TileDeep, libraries like Google's TensorStore, and some incredibly powerful open formats like ZAR and HDF5. Let's dig into a few of these, just to see how they operate under the hood. First up, ActiveLoop DeepLake. They actually explicitly market themselves as a quote-unquote tensor database for AI. And it's fascinating, because instead of storing data as your standard tabular records, it takes unstructured data. We're talking massive amounts of video, audio, and images, and stores them as tensors. The real magic here is that it's highly optimized to stream this high-throughput tensor data directly into PyTorch and TensorFlow data loaders right during GPU training. That means you can completely sidestep those annoying traditional disk bottlenecks. Then there's Google TensorStore. Google developed this as an open-source library specifically to handle massive, complex arrays across cloud storage. And when I say massive, I mean petabyte-scale, n-dimensional arrays. So if you're doing something like brain tissue imaging or trying to manage gigantic neural network weights that would literally crash a normal database in seconds, TensorStore is built to read and write that multidimensional data seamlessly at a staggering scale. Now, we also really need to distinguish between complete database management engines like TileDB and highly efficient open storage specifications like ZAR and HDF5. TileDB is this robust, universal array database engine handling everything from geospatial point clouds to complex biomedical genomics. ZAR and HDF5, on the flip side, are open formats. They aren't standalone databases themselves, but they provide a standard. This allows various query engines to chunk, compress, and super efficiently read arbitrary regions of multidimensional arrays that are just sitting out there in cloud storage. All right, bringing it all together in Section 4, the modern AI stack. So, with all this talk about highly specialized AI databases, you might be wondering, where exactly does our favorite analytical bird fit into all of this? Does a traditional SQL engine like DuckDB still actually have a place in this whole complex ecosystem? Oh, it absolutely does. An analytical engine like DuckDB flawlessly handles structured OLAP, tabular Parquet files, and even 1D vector similarity searches through extensions like VSS. DuckDB is fantastic for structured analytics, keeping track of your metadata, or even acting as a lightweight vector database. But, and this is a really critical but, it is not meant to store raw n-dimensional video tensors for model training. And this brilliantly illustrates the modern architecture. In the real world, smart engineering teams don't try to force every single workload into one magic tool. Instead, they pair a raw tensor store, maybe Deep Lake or a ZAR storage bucket for their heavy GPU deep learning data, and then they connect it perfectly with a structured lakehouse engine like DuckDB or MotherDuck. It's like a partnership. The relational engine acts as the brain for metadata, transactional catalogs, and structured analytics, while the tensor store just feeds that raw, multidimensional data straight into the algorithms. So, I'm going to leave you with this thought. As AI models increasingly move way beyond simple text to really understand our complex, multidimensional world of video, audio, and spatial data, is the super popular 1D vector database destined to become just a tiny footnote in your infrastructure? Because matching your data's actual dimensions to the right storage engine, that is the true foundation of your AI's future. Thanks so much for joining me on this explainer today, and as always, keep building.